In Hollywood movies, sniper scenes are often understated, since a sniper rifle can't hit a target point blank over a duration of 10 seconds. In reality, there are many factors and calculations that are required to deem a shot successful, thus taking time and patience in contrast to the films. So for this project, we'll explore how mathematics can be exercised under conditions such as gravity, wind speed, and the direction of the bullet while firing a sniper rifle. Before and during the 16th century, it was believed that all bullets travel in a straight, linear path until its speed was spent, thus dropping abruptly to the ground. This was believed to apply to all bullets regardless of its weight, mass, volume, or shape. In 1537, an Italian scientist by the name of Triglia discovered that bullets actually travel in arcs. This happens for two reasons. First, a gun is designed with two main components, the chamber and the barrel. When the gun trigger is pulled, a chemical reaction occurs in the chamber and gas is released. This will propel the bullet out of the gun. However, after leaving the barrel, the bullet will be deprived of its constant forward motion since the gas is no longer concentrated in the barrel. After the bullet leaves the gun, it's not only gas that contributes to the bullet's dipping path, but also gravity. Gravity is a constant force and remains the same on Earth. No matter what you do, objects will fall at the same rate. For example, if you dropped an object and tossed a similar object in an arc, they would hit the ground at the same time. Hence, with the knowledge of the gun anatomy and gravity's influence on the bullet, we can understand the bullet's flight when shot. The next condition which will be examined is the direction and the speed of the wind and its impact on a bullet's flight. For this purpose, we'll assume that wind is the only factor affecting the bullet. It's easy to counter the wind when the target is a negligible distance away, as the wind speed and the direction of it will have little influence on the bullet. However, this would not be the case if the target was a significant distance away, which is common for sniper units. To address this problem, we'll apply the Pythagorean theorem and trigonometry ratios to find out how we can hit the target. Here we have a sniper unit with his or her target a great distance away. Let's say that the bullet's speed while in flight is 900 meters per second. In windless conditions, the gun's position will not need to be adjusted, hence the angle x would remain 0. But what if we added wind? Given that the wind is about 100 meters per second, how does one counter its effects while shooting a bullet? In order to use all three trigonometry ratios to solve for x, we must first identify the value of the hypotenuse. Given the value of the two sides, we can continue with the Pythagorean theorem. Therefore, the value of the hypotenuse is approximately 905.54 units. Now that we have the value of all three sides, we can use all three trigonometry ratios to identify and confirm the value of x. The three ratios include sine, cosine, and tangent. Therefore, one can agree that the gun must be rotated 6.34 degrees towards the east to hit the target. Sniper units play a critical role in conflicts as they eliminate specific forces which would otherwise be difficult to target. However, the sniper unit would not be effective if not for the mathematics which allows each shot to be purposeful and effective. Through the use of gravity, wind speed, and the direction of the bullet, it is understood how math is a critical component that influences the success of a sniper unit.